So the last we talked about was Bernoulli's principle, and that's that an increase in the speed of a fluid occurs with a decrease in pressure or a decrease in potential energy. So think about it this way. When you crimp a hose, what happens whenever it gets to the other side of that crimp? Yep. It picks back up on the other end of the bend, right? Or you can even think of this as a narrow point in a river. Once it gets past that narrow point, everything opens to open back up again, and everything's rushing downstream. Sound about right? So that is Bernoulli's principle in a nutshell. So then we go to what's called Charles' law. Okay? And that, okay, something why that wasn't doing. So when the pressure of a sample of a dry gas is held constant, the temperature and the volume will be directly related. Okay? So when you have a single, how to say this? When you have a single pressurized container of gas, the hotter it is, the more it expands. The colder it is, the more it contracts. Like all things, yes? Air is no different. Okay? But the pressure is remaining the same, it's just taking up more volume. Now, why does that happen? Well, because heat causes all things to expand. So think about how a hot air balloon works. How does that work? It uses the heat to expand so that the air inside the balloon is less dense than the air outside it. Does that make sense? The air inside it is just molecules that are just constantly bouncing around, and they're so much less dense because they're so much more energized. There's just a certain volume of air that if you took all the heat away from that, there's not as much there. But because we heat it and we superheat it, it's so much less dense, and that's what allows a hot air balloon to go. So, yeah, there you go. Bit of a semi-physics lesson on that. Okay. That's why whenever you blow hot air into a balloon versus cold air into a balloon, which one's easier to blow up and which one has more volume? Hot air. That's why they say you're full of hot air. No, but that's the whole reason hot air expands more quickly is just because the heat is still being held in it. And then cold air contracts. That's why if you stick a balloon that is just full of basic air out in the cold versus in some place that's hot, the one in the hot area will probably expand a little. The one in the cold area will start to contract, start to lose volume. Does it make sense? All right, so then we have the Boyle's law. So this is the volume of a confined gas at constant temperature varies inversely with its pressure. So in other words, if we are not changing the temperature, volume and pressure are directly related. Does it make sense? Okay. So volume and pressure are directly correlated here. Uh-oh. Uh-oh. Apparently, whenever I tried to click on something, it decided it wanted to go do something. There we go. Okay. So with a rotary I love it when I cannot pronounce stuff. A rotary actuator or motor speed. In order to calculate this, you have to have the flow rate versus the displacement and rotational speed or velocity. Okay. I won't make y'all actually know this. This is just another formula you can use. But this part you definitely want to write down and know, and that is the basic parts of a hydraulic or pneumatic system. Now, just like with electricity, what do you have to start off with something called something in electricity? You have to have some sort of power, right? You have to have some form of jumping off point. You have to have something that starts everything going. Does that make sense? And you have to have some form of an output. You have to have some sort of end game down the line, right? With electricity, you have to have a resistor or some sort of something that's going to use that power down the line. Everybody know what I'm talking about? Everybody understand? Okay. What's different is that with electricity, you don't have to have something to control your anything, right? You don't have to have some form of control. However, with hydraulics and pneumatics, if you don't have some form of control over what's going on, you're not going to be able to do anything with it. Control is not a non-negotiable with this. It's the easiest way I can say that. All right, so you have to have a supply, control, and output. Those are the three major parts that you have to have. So with a power supply, you have to have some form of a prime mover. This is either counted as an electric motor, something that's going to constantly kick on and run, or a combustion engine. This is what you would find at something like a job site. These are the gas-powered pumps or the gas-powered compressors on a job site, so everybody can use power tools. So the very definition of a pump is something that's going to convert mechanical power to hydraulic power. So this is what is the prime power supply for hydraulics, is some form of a pump. Okay. And then you have a compressor. This is by definition for pneumatics alone. Why? Because technically you cannot compress a liquid. It doesn't like it. You can compress air. You can do that all day long. But you cannot compress a liquid. That is why we breathe air, not water. Well, at least most of the year. When it starts to get muggy out like it did today, all bets are off. You have to have some form of output. No matter what kind of circuit you're dealing with, you always need to have an output. Somewhere, some way, somehow. Okay? And we do that with hydraulics and pneumatics through actuators. These convert fluid energy into motion to move a load or to do something at the very end of what it's trying to do. It's for pneumatics and hydraulics. It works for both. The whole thing about pneumatics and hydraulics is that they are very close. They're just about cousins. Okay, they're that close on the family tree. They're almost brother and sister sometimes. In most applications. The thing about hydraulics that's so different from pneumatics is that hydraulics deals with a fluid that is incompressible. Okay, you start putting hydraulics under too much pressure and they can and will leak around the seal and all that. But the thing about hydraulics is that they're the workhorse. They can do a lot of work with a very little effort. Pneumatics has to put a lot of effort into not as much workload. But the types of actuators, you have a linear actuator, a rotary, and a motor. Now the difference between a rotary and a motor is I don't know how many of y'all remember the old rotary phones where you put your finger in the number, you turned it all the way, then once you pulled your finger out, it snapped back. It didn't rotate a 360, it rotated maybe 180, right? Same with a rotary actuator. It doesn't rotate all the way. It can do a half rotation, quarter rotation, whatever it needs to do, versus a motor that, just like the motor in your car, it continually sits there and spins. Does that make sense? Okay. So that's our output. So we have our input and our output. So somewhere in the line, we have to have a control. So for a control, this is what changes the direction, the pressure, and the flow rate. So everything that is not a power supply or output is a control. Everything, except for maybe the piping or tubing. But that's just a way to get it from point A to point B. So to talk about it in electrical terms, this is your light switches, it's your diodes, transistors, LEDs, things like that, right? So your outputs for most of those would be something like a light bulb or a motor for electricity. Your inputs is basically either you're getting it from the power company or you're getting it from a battery, right? So they're not all dissimilar. What flows in electricity? Electrons. You're making electrons flow. Here, you're making fluid or air flow. And it all does it to do a job. Does that make sense? And then everything else is a control. So with components, you have to have a filter or silencer on a lot of air. We have silencers, or they can also be called a what? What's on your vehicle that muffles the noise? It's a muffler. There's several names for this particular part. Filters. You have to have filters constantly on a lot of these. Why? Because if it's air, we don't want pollen, the evil yellow death cloud that comes about this time of year, to mess up the internals of any of our systems. And for anything that's a fluid, we really don't want contaminants in our fluid because that would be really bad on the components that go with it. You have compressors or pumps. Compressor is pneumatic, pumps hydraulic. Compressed air can get really, really hot because you're basically forcing a bunch of molecules together, so they start bouncing off each other. So one of the things we can add to a pneumatic situation is what's called an aftercooler. And this just takes any hot air that's coming out of your compressor and brings it down to a cooler level so that you don't end up heating up components, because heat is actually quite the enemy for us, isn't it? Why is heat the enemy? Hmm? Heat destroys, right? Heat is not our friend when it comes to making all things stay together. Heat causes corrosion faster, it causes things to break faster. That's why we don't typically heat a factory. Generally, any heat that's produced in one of those is self-produced. A lot of the typically stays around 70 degrees. We try and keep any and all components cool, kind of like a computer. Don't want to overheat a computer because it'll start tearing up the components inside. Separators do exactly what they sound like. They can separate. You can have it in air to, well, I'm sorry. All of a sudden, I'm having a very hard time with that one. A separator does exactly what it says it does. It's able to separate good things from bad things, or separate one part from another. Pressure switches, again, exactly what it says. It's a pressure switch. That can either be an internal pressure switch or an external pressure switch, depending upon what you're trying to set up. Do you want to be able to control it, or do you want the fluid to control itself? Or the air to control itself? Relief valve. This is on every system, no matter what. Why? To release pressure, exactly. Pressure relief valves are probably one of the most common parts on hydraulics and pneumatics. Why? Because if you overpressurize hydraulics, you're going to blow your seals, and that's a really hard thing to replace. Think about your car. If you blow the seals on your car, how hard is it to get into every single seal in your car and replace those? You are looking at a lot of shop time and a lot of shop money, and you might as well just replace the vehicle. And same thing goes for pneumatics. If you end up blowing out your seals in pneumatics, you're going to have that same kind of issue. You're going to have to crawl through everything to make sure which seals are good, which seals are bad, what's cracked, what's broken, what's not. It's just not worth it. You have relief valves for that reason. Hydraulics specifically have to have some form of a reservoir or tank. You can have them with air compressors. You don't always have to have them with the compressors, but you have to have some form of it with a hydraulic system. If you have one with a compressor, it stores air so that you don't have to as long to wait for more compressed air. Does that make sense? It's kind of like it works like a hot water heater. How's your hot water heater work? Well, it sits there and it keeps hot water sitting in that tank, and then you turn on and ask for hot water somewhere in your house, and it sends it out. You don't have to wait 20, 30 minutes for it to heat the water to the temperature you're wanting, right? Same thing for hydraulics and pneumatics. With hydraulics, you have to have that tank because otherwise you're pretty much pouring liquid out everywhere. That's never a good thing. With pneumatics, it's Same principle as a hot water heater. Like I said, it's all meant to just keep a pressurized air staying in that tank. And you start using it, the pressure regulators kick on, and all of a sudden you have more air being compressed and the pressure remains. But you don't have to wait 20, 30 minutes for the air to compress enough that you have the ability to use your tools. Does it make sense? More or less. Lubricators, lubrication filters, pressure regulators assemblies. These are, again, completely typical on any and all hydraulic and pneumatic systems. We add lubrication to a lot of air systems. Why? What do we want to make sure does not dry out? We don't want our parts to dry out. We want them to stay lubricated, and we want them to stay have oil in them so that they don't end up catching friction burns, because friction kills any and all components. Yes? With hydraulics, we don't have to worry about it. It is a lubrication fluid in and of itself. With pneumatics, we typically are pulling every last little bit of anything that could possibly be in their system out of it through a bunch of filters, right? Which means the air is very dry. So think about air during winter time. What happens to your skin, to your lips, and everything else during winter that doesn't happen during summer when everything's nice and hydrated? Everything dries out, everything cracks, everything starts to bleed, right? So if you have oil in an air system, if you don't have oil in an air system, everything's just dry. So what's going to happen to your seals over time is they'll deteriorate faster. Your components will deteriorate faster. So what do? You add just a drop of oil every now and then. It vaporizes into the air and it finds its way to each component, and hey, it's lubricated, everything's good. It lasts longer that way. Regulator assemblies are what you'll be seeing in there. They're basically what the pressure gauge, and they actually have a moisture filter on them as well. We'll talk about that when we get there. Directional control valves, another name for these, or the short initials for these that are typically used, are a DCV. DCVs, because directional control valve is a mouthful, do exactly what they say. They control the direction of your fluid, whether it's a hydraulic or pneumatic fluid. It's directing it to where it needs to go so it can do the job it needs to do. We already talked about what an actuator is. It's something that's going to take the fluid power and do mechanical, physical work. Okay? Piping, that's, again, kind of self-explanatory there. Piping is how you get your fluid from one place to another. I don't care if it's hydraulic fluid or air. It's got to have some form of way to get to where it's got to go. And then you have regulator valves. And these, again, kind of self-explanatory. They regulate the air pressure, or they regulate some form of what the air or fluid is trying to do. So, questions on this, guys? All right. So hydraulic, power through liquid. Pneumatic, power through gas. Hydraulic fluid is not compressible. Why? Because if you start really compressing on hydraulic fluid, it's going to leak like crazy. However, air does not mind being compressed to some degree. However, if you overcompress air, it will start to form bonds with each other. Hydrogen, helium, oxygen, those and nitrogen all like to bond to other atoms. Not generally a good thing when it does. Hydraulic offers a lot of high power options. It can do thousands of pounds of work. It is why we use them for everything from a car crusher to amusement park rides to, you can use them for anything. They're high power. Pneumatic is low power. Hydraulic tends to have a very smooth response. Pneumatic tends to be fairly quick. Why? Because once the air starts moving, it's got to move. It doesn't like to stall out very much. And then hydraulic, you have precise positioning versus moderate precision. In other words, I can put hydraulics anywhere I want to. All I gotta do is shut off the flow of fluid. That's not gonna move because it's not what? This word right here. Non-compressible. If I cut off the fluid flow into or out of a hydraulic component, it's not gonna move because it's not compressible. Pneumatics can have some bounce to them. Hydraulics don't. That's why hydraulics are so precise, pneumatics really not so much. Think about it like a balloon. If you put water in a balloon versus air in a balloon, which one do you have to worry more about popping? The water one. Why? Once it gets to a certain place, it's going to bust. But I can put however much amount of water in there and it's going to stay there perpetually forever and ever, amen. It won't leak, right? As long as you take proper precautions, of course. With pneumatics, what happens to a balloon that's, let's say, 5 days old that's got air in it versus a balloon that's 5 days old that's got water in it? Mm-hmm. If you've done the right things, the water will not, all right? That's why pneumatics is moderate precision. Hydraulics is very precise. Hydraulics don't go anywhere. All right, and then here's a summary out for y'all. Some things you might want to look over either in your book or just kind of keep in mind in your notes. Pascal's law, the different types of fluid flow, the 3 sections of fluid power systems, what is power, what is fluid power, horsepower. Like I said, Bernoulli's and Boyle's law, just kind of keep those in mind. Any questions? All right, so one of the things I was going to show y'all real quick, I think I finally got that one settled. Apparently not. Never mind. I'll make sure it's taken care of later. All right.